When assessing a part winding start motor system, several factors should be taken into account. Firstly, motor specifications should be reviewed. The motor specification should explicitly indicate whether it's designed for part winding starting. Secondly, consult the manufacturer's instructions. Always adhere to the manufacturer's guidelines for the correct winding sequence and overall operation of the part winding starter. Thirdly, consider the load characteristics. A centrifugal pump typically exhibits low inertia and friction. This characteristic can significantly influence the effectiveness of part winding starting. Now, let's explore possible causes if the motor fails to rotate during the initial starting sequence. One potential issue is an incorrect winding sequence. Double-check that the windings are connected in a precise sequence specified by the manufacturer. Another possible cause is an excessive load. If the pump is connected to a system with high pressure or a fluid with high viscosity, the increased load could prevent the motor from rotating solely in the first winding. Electrical faults could also be the culprit. Thoroughly inspect for any electrical faults like open circuits or short circuits, as these can severely disrupt the proper operation of the part winding starter. Regarding evaluation and recommendations based on the information, it's conceivable that the motor's failure to rotate during the first starting phase could be normal behavior for a part winding motor connected to a centrifugal pump load. However, it is imperative to consider the following points. Firstly, analyze the current inrush. If the inrush current during the second starting phase remains excessively high, it might be wise to explore alternative methods for reducing it, such as implementing a soft start controller. Secondly, consider the specific application requirements. Carefully evaluate the demands of the specific application and determine whether part winding starting is truly the most suitable method for initiating the pump. Thirdly, verify the manufacturer's warranty. Ensure that the manufacturer's warranty provides coverage for a motor's operation when using a part winding starter. Given these factors, make an informed decision about whether to accept the system as is or propose alternative solutions to guarantee proper and safe functionality. Seeking advice from the manufacturer or an experienced electrical engineer could provide further clarity and guidance. Now let's delve deeper into the technical considerations of part winding starters and their application in motor control systems, particularly focusing on fire pump systems. Part winding starting is a reduced voltage starting method used to limit the inrush current during motor startup. It achieves this by initially energizing only a portion of the motor's windings. This reduces the initial current draw, lessening the stress on the electrical distribution system and minimizing voltage dips that could affect other equipment. The typical motor designed for part winding starting has two identical sets of windings. During the first stage of starting, only one set of windings is energized. This reduces the applied voltage and consequently the current. After a short delay, the second set of windings is energized, bringing the motor to full voltage and speed. However, the effectiveness of part winding starting depends on several factors, including the motor design, the load characteristics, and the specific application. In the case of a 40 horsepower, 208 volts motor driving a centrifugal pump, several issues could arise. Firstly, the motor itself must be specifically designed for part winding starting. Standard motors cannot be used with this starting method, as it could damage the windings. The motor's nameplate should clearly indicate that it is suitable for part winding start. Secondly, the load characteristics of the centrifugal pump play a crucial role. Centrifugal pumps typically have a low starting torque requirement, which makes them suitable for reduced voltage starting methods. However, if the pump is connected to a system with a high static head or if the fluid being pumped is particularly viscous, the starting torque requirement could be higher than anticipated. In such cases, the motor might not be able to accelerate to a sufficient speed in the first set of windings alone, leading to the observed behavior of no rotation during the first stage. Thirdly, the control circuit for the part winding starter must be properly designed and configured. The timing of the switch from the first set of windings to the second is critical. If the delay is too short, the motor might not have enough time to develop sufficient torque, and the inrush current could be similar to that of an across-the-line start. If the delay is too long, the motor could stall or overheat. Fourthly, the condition of the motor and the pump must be considered. Worn bearings or other mechanical issues could increase the starting torque requirement and prevent the motor from rotating on the first set of windings. Similarly, a clogged impeller or other obstructions in the pump could also increase the load on the motor. Now let's discuss the inrush current and its implications. The primary goal of part winding starting is to reduce the inrush current compared to an across-the-line start. In an across-the-line start, the motor draws a large amount of current, typically 6 to 8 times the full load current, during the initial starting period. This inrush current can cause voltage dips in the electrical system, which can affect the operation of other equipment. Part winding starting reduces the inrush current by initially applying a lower voltage to the motor windings. However, if the motor does not rotate in the first set of windings, the inrush current during the second stage could be significant. When the second set of windings is energized, the motor essentially experiences a second inrush current, which could be similar to that of an across-the-line start. This is because the motor is already under a load and is not yet up to full speed. To accurately assess the inrush current, it is necessary to use a clamp-on ammeter or a power quality analyzer. These devices can measure the current during the starting period and provide valuable data for evaluating the effectiveness of the part winding starter. If the inrush current is still excessive, even with the part winding starter, other reduced voltage starting methods should be considered. These include auto transformer starting, reactor starting, and soft starting. Auto transformer starting uses an auto transformer to reduce the voltage applied to the motor during starting. This method provides a more controlled reduction in voltage compared to part winding starting and can be adjusted to optimize the starting torque and inrush current. Reactor starting uses a reactor in series with the motor windings to reduce the voltage during starting. This method is less expensive than auto transformer starting but provides less control over the starting torque and inrush current. Soft starting uses solid-state devices to gradually increase the voltage applied to the motor. This method provides the most controlled starting and can significantly reduce the inrush current. Soft starters also offer additional features such as overload protection and undervoltage protection. Now let's talk about the NEMA MG1 standard, which is the National Electrical Manufacturers Association standard for motors and generators. NEMA MG1 does address part winding starting and provides guidelines for its application. However, the standard also acknowledges that some motors may not rotate in the first set of windings during part winding starting. This is particularly true for motors connected to high inertia loads or loads with high static friction. The standard emphasizes the importance of verifying the motor's performance with the specific application and load. If the motor does not rotate in the first set of windings, it does not necessarily mean that the part winding starter is not functioning correctly. However, it does indicate that the starting torque might be insufficient and other starting methods should be considered. Now, regarding the specific case of a fire pump system, it is crucial to ensure that the starting method is reliable and complies with all applicable codes and standards. Fire pump systems are critical for life safety, and their performance must be guaranteed. The National Fire Protection Association NFPA 20 standard for the installation of stationary fire pumps provides detailed requirements for the electrical supply, control, and starting of fire pump motors. NFPA 20 requires that the fire pump motor be capable of starting and running under full load conditions. The standard also specifies the maximum allowable voltage drop during starting. If the voltage drop is excessive, it could prevent the motor from starting or cause it to stall. Therefore, it is essential to carefully evaluate the electrical system and ensure that it can support the fire pump motor starting requirements. In addition to NFPA 20, local codes and regulations may also apply to fire pump systems. These codes may specify additional requirements for the starting method, such as the use of a specific type of reduced voltage starter or the need for a backup power supply. To determine whether to accept the fire pump system with the part winding starter, several steps should be taken. Firstly, verify that the motor is specifically designed for part winding starting and that the motor's nameplate clearly indicates this. Secondly, measure the inrush current during starting using a clamp-on ammeter or a power quality analyzer. Compare the measured inrush current to the motor's full load current and the allowable voltage drop specified in NFB 820. Thirdly, evaluate the starting torque requirement of the centrifugal pump. This can be done by consulting the pump manufacturer's data or by performing a site test. Fourthly, inspect the control circuit for the part winding starter and ensure that it is properly designed and configured. Verify that the timing of the switch from the first set of windings to the second is correct. Fifthly, check the condition of the motor and the pump. Look for any signs of wear or damage that could increase the starting torque requirement. If the inrush current is excessive, the starting torque is insufficient, or the control circuit is not properly configured, the part winding starter should not be accepted. In such cases, other reduced voltage starting methods should be considered, such as autotransformer starting, reactor starting, or soft starting. It is also important to consult with the fire pump manufacturer and an experienced electrical engineer to determine the most appropriate starting method for the specific application. Ultimately, the decision of whether to accept the fire pump system with the part winding starter should be based on a thorough evaluation of the electrical system, the motor, the pump, and the applicable codes and standards. The safety and reliability of the fire pump system must be the top priority. Let's look into some further aspects related to motor protection and coordination in fire pump applications. Motor protection is vital to prevent damage to the motor due to overloads, short circuits, and other electrical faults. Fire pump motors typically require specific protection schemes to ensure reliable operation under emergency conditions. Overload protection is designed to protect the motor from overheating due to excessive load. This is typically achieved using thermal overload relays, which sense the motor's temperature and trip the motor circuit breaker if the temperature exceeds a safe limit. However, fire pump motors often have different overload protection requirements compared to standard motors. NFB 820 allows for reduced overload protection for fire pump motors to ensure that they continue to operate even under overload conditions. This is because it is more important to keep the fire pump running during a fire emergency than to protect the motor from damage. Short circuit protection is designed to protect the motor and the electrical system from damage due to short circuits. This is typically achieved using fuses or circuit breakers, which interrupt the flow of current in the event of a short circuit. Fire pump motors require specific short circuit protection to ensure that they are quickly disconnected from the power supply in the event of a fault. Coordination is another important aspect of motor protection. Coordination refers to the selective tripping of protective devices to isolate faults and minimize the impact on the electrical system. In a fire pump system, it is crucial to ensure that the protective devices are properly coordinated to prevent nuisance tripping and ensure that the fire pump motor continues to operate during a fire emergency. Now let's delve into the power supply requirements for fire pump systems. The power supply for a fire pump system must be reliable and capable of delivering the required voltage and current under all operating conditions. NFB 820 specifies detailed requirements for the power supply, including the voltage regulation, fault current capacity, and backup power supply. The voltage regulation of the power supply must be within acceptable limits to ensure that the fire pump motor can start and run under full load conditions. Excessive voltage drop can prevent the motor from starting or cause it to stall. The fault current capacity of the power supply must be sufficient to allow the protective devices to quickly interrupt the flow of current in the event of a short circuit. A backup power supply is often required for fire pump systems to ensure that they continue to operate even during a power outage. The backup power supply can be a generator or a separate utility feed. The backup power supply must be capable of supplying the required voltage and current to the fire pump motor and must be automatically switched on in the event of a power failure. Now let's discuss the grounding requirements for fire pump systems. Proper grounding is essential for the safety and reliability of the electrical system. Grounding provides a low impedance path for fault current to flow back to the source, allowing the protective devices to quickly interrupt the flow of current in the event of a ground fault. NFPA 70, the National Electrical Code, provides detailed requirements for grounding electrical systems. Fire pump systems must be grounded in accordance with NFPA 70 and any applicable local codes and regulations. The grounding system must be properly designed and installed to ensure that it can effectively carry fault current and protect personnel from electrical shock. The grounding electrode system for a fire pump system typically consists of a ground rod or a ground plate connected to the building's grounding system. The motor frame, conduit, and other metal enclosures must be bonded to the grounding system to provide a low impedance path for fault current. Now let's cover the control wiring for fire pump systems. The control wiring for a fire pump system must be reliable and resistant to fire and water damage. NFPA 20 specifies detailed requirements for the control wiring, including the type of wire, the routing, and the protection. The control wiring must be suitable for the environment in which it is installed and must be protected from physical damage. The control wiring must also be fire resistant to ensure that it continues to function during a fire emergency. The control wiring for a fire pump system typically consists of a combination of power circuits and control circuits. The power circuits supply power to the motor, while the control circuits provide control signals to the starter, the pressure switch, and other components. The control wiring must be properly labeled and identified to facilitate troubleshooting and maintenance. Now, let's talk about the acceptance testing of fire pump systems. Acceptance testing is performed to verify that the fire pump system is properly installed and functioning correctly. NFPA 20 specifies detailed requirements for acceptance testing, including the tests to be performed, the equipment to be used, and the acceptance criteria. The acceptance testing typically includes a visual inspection, an electrical test, and a hydraulic test. The visual inspection is performed to verify that the equipment is properly installed and that the wiring is correctly connected. The electrical test is performed to verify that the motor, the starter, and the control circuits are functioning correctly. The hydraulic test is performed to verify that the pump is delivering the required flow and pressure. The acceptance testing must be performed by qualified personnel, and the results must be documented in a written report. The acceptance testing is a crucial step in ensuring that the fire pump system is reliable and will perform as intended during a fire emergency.